So welcome to the final lesson of the unit on light. We are talking wave energy today, and the question of the day, what is the speed of light in meters per second and nanometers per second? And then what variable represents the speed of light? We are getting into the part of chemistry that is sort of overlapping with physics, and it's sort of a matter of opinion whether it's chemistry or physics. If we were to really dig down, all of this is sort of like quantum mechanics. We're getting into the physics inside of atoms is more or less what this is. So there's a bunch of scientists, we're talking like the early 20th century, and there's just like crazy amounts of good science happening at this point. This is like Rutherford is going on with his gold foil experiment. We're not too far off from Niels Bohr. Marie Curie, you'll learn about her later in the nuclear unit. She's hot at work right now. So a bunch of scientists, Albert Einstein is mixed in this, Heisenberg with the uncertainty principle. It's like a beautiful time to be a chemist / physicist. And there is this idea that light, electromagnetic radiation, is acting like a wave, right? But in some cases, we sort of see it acting like it's a particle, like maybe it's an electron. So this is like where the idea of a photon comes from. A photon is a light particle. As far as we know, it has mass, but not really. It's a little like the gray area of like what's going on. This still needs to be explored. It's a particle of light. And it is going to contain a little pocket of energy. And that is called a quantum. Multiple of them would be called a quanta. And they are only going to exist in whole numbers, the same way protons, neutrons, and electrons exist only in whole numbers. And this is part of what gives us this idea that like it might be a particle, is that it only comes in whole numbers. There is also the concept of a black hole, right? Out in outer space, we have these black holes, and they appear to suck in light by the force of gravity. So we assume that the black hole has something super, super massive that is able to attract things by gravity. So you may have learned in earth science, maybe some physical science classes, that gravity, like on Jupiter and Saturn and the sun, is a lot stronger than it is on Earth because those celestial bodies, whether it be a star or a planet, is bigger. The bigger it is, the more gravitational pull it has. The gravity on the moon is smaller, less significant than on Earth because the moon is smaller than the Earth. Okay, so the black hole has so much gravity, we have to assume that it's really, really big, really dense, has a lot of matter, has a big mass, and is able to pull in light. You'll actually, like with good photos, you can see the light kind of spiraling into a black hole, sort of like water going down a drain. So this also helps us to kind of say a photon might be a particle. It's sort of a gray area, and we have some evidence to kind of back this up. But it's something to be explored. So if you're interested in this for real, you would want to get into quantum chemistry, astrophysics. It's kind of crazy how like the inside of an atom behaves sort of the same way as all of outer space. It's just nature repeats itself, and it's pretty cool. So one of these scientists in the early 20th century is Max Planck, and he is doing a bunch of physics, calculus, math, experimenting, and he determines that the energy of one photon would be equal to its frequency times this crazy number, 6.626 times 10 to the negative 34th joule seconds. And that happens every single time. So it's a constant. It's just a constant of nature. Really, what he's finding is the relationship between energy of a photon and its frequency. That's all. That's all you need to know. The energy of a photon and its frequency is related to each other by the term that he called Planck's constant. Of course, he named it after himself. That is 6.626 times 10 to the negative 34th joule seconds. So energy is going to be measured in joules, the energy of this photon. We're going to multiply that by, that would be equal to Planck's constant, the relationship between energy and frequency, times the frequency in hertz. Energy is joule is a unit of energy. It's a metric unit, so we can convert it into kilojoules or millijoules. No one does that. Once you get down to really, really tiny things, people start using something called electron volts. That's more of a physics term. In chemistry, primarily you're going to be using joules, occasionally kilojoules in this case. So this can be applied to any type of light, because remember, we're talking about photons here. So this would not be true for a sound wave or a beach wave. This would only be true for a light wave, because specifically we're talking about the relationship of the energy of a photon to its frequency. Okay, so light doesn't just mean visible light. It could mean anything on the electromagnetic spectrum. Why do chemists have terrible naming conventions? I'm not quite sure, but light means anything from radio to gamma waves. You will find the longer you take chemistry, the more you realize that chemists are terrible at naming stuff. So if we have the frequency of anything on the electromagnetic spectrum, which we usually do, we can figure out the amount of energy associated with that wave. Mathematically, we're just going to adjust this equation, would be equal to the velocity divided by the wavelength. We can plug that in to this Planck's equation, and we get this one on the right, which is what you'll see most often. The energy is equal to Planck's constant times its velocity divided by the wavelength. Okay, so all we did was take the equation from wave speed, frequency equals velocity divided by wavelength, and plug it into Planck's equation. It's not really called Planck's equation, but we can call it that. And then we get this substitute, E equals hv over lambda. Now, remember, in the case of Planck's constant, we're talking about photons. We have to be talking about light waves. So you'll often see this equation as E equals hc over lambda, because just like I said in the last lesson, c is a more specific version of v. V is just vague velocity. C means the speed of light. And in the case that we're talking about photons, we have to be talking about light. So plugging in a c probably makes a bit more sense. But I wanted you to see that we can also show it as v, because the equation I gave you in the wave speed lesson was v or c, but v. So we have the speed of light for c. Now here's like a sample question where this would come up. What is the energy of a sample of blue light if its wavelength is 480 nanometers? Okay. Let's backtrack a little bit. What is the energy? That means I have to use Planck's constant somehow. I know that I'm working with visible light, so blue light, photons, that also is going to kind of reiterate that I need to use this Planck's equation. And my wavelength is 480 nanometers. So 400 to 800-ish, it kind of varies. That is our visible spectrum. So again, visible light. It looks really scary. I promise it looks far scarier than it actually is. If you know how to use a calculator and use it well, this is not scary at all. I need to find out the energy, so I'm going to solve for E. H is a constant. It's a scary looking constant, but it's just Planck's constant. And Planck's constant is the relationship between frequency and energy of light. That's all. So we're going to plug in that number for H. C is super easy because I know the speed of light. It's also a constant. In this case, I chose to use 3 times 10 to the 8th. You could have plugged in 3 times 10 to the 17th because we're working in nanometers. That's fine as well. And then we're going to divide by the wavelength, which we got from the question. So as long as you are careful with your parentheses in your calculator, it's really not going to be bad. For my final answer, I'm getting 4.14. For the sake of sig figs, I'm just chopping it there because after comes a 1 and I'm not the 1 doesn't kick up the 4, it just leaves the 4. So I get 4.14 times 10 to the negative 19th. Now, the calculator doesn't tell you, hey, you calculated energy, so do this in joules. You have to know that you have done an energy calculation and your unit is joules. This is really it. This is energy of a wave. When it comes down to it, there are plenty of examples where you will use these equations, all of them, to calculate the frequency of a wave, the energy of a wave, the wavelength of a wave, the speed of a wave, even. Now, most of the time, the speed of light is 3 times 10 to the 8th meters per second, or 3 times 10 to the 17th nanometers per second. I just want you to know that when light travels through glass, or it travels through glass and then it travels through water, it is going to slow down a touch. So you may come across questions where it says, light travels through a glass of water or a beaker of water or through a prism, and it's going to slow down a touch. So in that case, you would be solving for c, the speed of light in that case, although this is why I like using v, because in my mind, v is just velocity and c is always that constant of 3 times 10 to the 8th meters per second. It's just algebra from this point. If you have issues beyond this point, it's just algebra problems, which is okay. It's okay to have algebra problems. Nobody, especially when you're working with these scientific notations and all the parentheses, it's very easy to get scrambled. But I will tell you, the more practice you get, the more comfortable you will be with this, especially when it comes to those exponents. Because if you plugged all of this in and you're getting that the energy of a wave is really, really big, that can't be true. The energy from a sample of blue light with an itty bitty teeny tiny wavelength is going to be really tiny. If you look at Planck's constant, we're looking at times 10 to the negative 34th joule seconds. That is a crazy tiny number. Crazy tiny. So that means that your answer is going to also have to be crazy tiny. Again, the more you work with it, the more comfortable you'll get. Energy often is going to be a negative exponent in the high teens. Frequency is a positive exponent in the low teens. Your wavelength, depending on if you're working in meters or nanometers, we're looking at, times 10 to the 8th, and then times 10 to the negative 7th. Just trust me, the more practice you get, the more comfortable you'll be with it. That's all. If you have any questions, feel free to leave them in the comment section below the video. I will, at some point, really no promises, try to get a video out practicing some of these calculations, because I know that they can be really, really tough. This is more or less like just the concept of it, and then go do the algebra. But I would like to give some algebra help for those who need it. So I will get that done at some point, probably within the next 365 days. If you have any questions in the meantime, feel free to leave them in the comment section below the video. Subscribe so you don't miss the next lesson, and I will see you there. Bye.